The sound's not working. Okay, that should be my computer. That should work. It works. And that looks like it's also working. Okay, hopefully that works and people will let us know if it continues not to work. Okay, well, where was I? This is my favorite part of recording all these meetings, is that we get all this valuable content. Our biggest announcement is our upcoming symposium, May 16th, back at the Seattle Art Museum. The title is Future-Proofing Building Enclosures, Improving Building Design and Product Practices Today for a Better Tomorrow. Sponsorships are available. Talk to Bobby if you're interested in sponsoring. If you haven't signed up for a table already. I meant to make the font bigger on this. Our keynote speaker is David Zach, who's a futurist. We also have Brian Rich from Rich Haven Architects talking about the principles of future proofing. Energy codes panel with Dwayne Johnlin. Emerging trends in high performance building enclosures by Dan Overby from Ball State. And future proofing mass timber with Graham Finch from RDH. A few other area events. Puget Sound has their prospect. Puget Sound CSI has their prospect coming up in March. CSI is doing a regional conference in Bellingham on May 4th through 6th. And then IBEC has their international convention and trade show in Houston. Additionally, Brian Rich, who I mentioned, is speaking at our symposium, is also helping to put together this the architectural preservation future of technology, environment, culture, and heritage. They have a call for abstracts coming up, and then that will be in September in Seattle in October. Our research grant applications are open. That's also managed by Grace Wong. And we're looking for projects in the area to promote building science that we can give some funds to. And then I'd like to bring up Brian from Overcast, who is our sponsor.
Yeah, I appreciate it. Bingo. Is there a one up there?
Yeah, if you want.
I don't think this works with the room. I don't know if it works with online. Yeah, okay, great. Hello, everyone. My name is Brian Himmelsdown with Overcast. And Overcast is a division of history. I saw our name on the wall out there. And we're part of the Innovation Center. And if anyone's ever been over there before, a great place where we house a number of companies that are hoping to keep history at the forefront of innovation. And we'll go to our first slide, but basically it's, we're kind of challenging the broken systems that are on the design side today and also on the construction side through a way to simplify overhead and pieces. So my first slide up here says we're building enclosures and design systems. They're related, but they're kind of unrelated. We're in the same room, but we're really not talking to each other like we could be. During the early schematic phase, etc. You guys are trying to figure out if they're bringing gear in and out for modulating the inside. And traditionally, our design and construction has been kind of backwards. But our designers, or the designers on the VDC side and the architecture side, they are basically designing throughout the whole construction life cycle, the VDC processes, etc. Because they haven't validated all the systems. The construction side, they're out on ladders, and there's probably 150 ladder planks in every room, and we're not going to change that. And basically, we came up with a platform that will help buildings be more intelligent, sustainable, and also affordable. So we have value engineered a platform that we show you here. It's kind of new in the marketplace. We've been around for about 4 years, but we're just now really pushing out. And we think it's a better way to, well, since it's modular and it's it's more adaptable. So there's a first, life saving cost and a second cost also. Sorry, I only have a few minutes, so I'll just kind of try to.
Sorry.
Yeah, here's a picture of our clouds, the first version of it. We're at 2.5 now. And basically what you see, I normally ask people what they're, what they see here, but for the time saving, we developed a project together with Owens Werman, and it's called the Atlas Building. We don't have one? Or both of them are the same. They're CLT projects, and the company owners decided to get together and invent a way to help minimize our systems of above, but between that roof back effect coming down. And created this platform called Overcast, which incorporates basically the lighting, IoT devices, all the sensors, and the MEP. And sometimes it doesn't include the HVAC, sometimes it's everything else. Maybe we'll jump together tonight. So again, we're simplifying it. The commission is different because we have direct OEM relationships with our suppliers. So that's different also. And so instead of a light costing $200, and then getting jack up to $1,000, we're going to keep that and pass on that savings. It's very interesting. So we don't install these, which is design and manufacture them, and then we push these platforms out at the end of the life cycle of a building, and then GCs actually install them with the interchanging of two ladders, and that's what you see with that box, and that's probably. Well, our most recent project was the UW Milgar Hall, and this is construction that this was set up. So, and again, it offers just a lot of adaptability, and I think about that with building enclosures, like usually like this building, this is an entry project, so I can't say anything bad about it. It's beautiful, but I can imagine our clouds in here, and usually you don't get a choice if there's, if there's a cold spot or something like that, and you want to move things around. And with traditional systems, with already. So I'm going to look at this slide. So our clouds are basically where people congregate in buildings. We're in probably 60% of the building overall. There's our cloud on the right, and then there's flying, which is a multi-race raceway. Next one. Kind of what I talked about earlier, we push all the design decision making very forward in the design process. So we will bring in, the Siemens guys at the very end, let them figure out where everything's going to be. We get everything designed in through our tech panel that we'll show here in a second. Supply chain, I talked about that. Perfect. There we go. So on the right hand side, this is the top side of our panels. And you can see the lighting, basically one point of contact for all of our systems. And then on the left hand side, you can see basically the three elements, all the tech lane in the middle there, the acoustic panels. If it's a CLT project, then we have the lighting on the outer edges. So this is something we just invented. It's basically this tech lane, and now we have removable pieces. So maybe later on in school, you want to incorporate, we were talking about the security system today, if you want to add cameras or fake detection, all that good stuff, other sensors, we can just search the panels, those systems, and then add these as we go along the time. I'll just skip this one. This is just kind of shows how we get involved with owners and this system very quickly. Yeah, so there's the three different systems. If you've got an OEM relationship with someone, and you want to incorporate that, it's going to take longer, it's going to be more expensive, but we can incorporate it. Otherwise, we don't want to end up what happened with Terra, and we're just minimizing all the other systems.
Okay. Some of these are auto jumping. I'm not clicking ahead of
it. So, for the most part, our systems are they're hung down through threaded cable, but we can incorporate it into the grid also. So the next one, lots of different health fairs, and I'm just going to end with all the different types of markets. Higher ed has been our biggest push. Healthcare is number 2. It's coming on very, very strong. And we'll go a couple of slides. So classroom auditorium, I think this match on the case work here Yeah, I think we are incorporating the MEP there with what's down below. And K through 12, we've kind of dropped down, we're in grid, but we've dropped it down as an architectural element. Here's one that Bobby never talked about. He worked on this project. This is a joint venture between UW and Gonzaga. It's obviously an hour lab. And so we can even put lighting in our files and put it on down. Another life science, which is actually the smart as I mentioned, has come on strong. This one's great because we've got a service panel above, and people are going, God, over this, which is minimizing all the systems stay below. If you got whatever repeatable spaces, maybe like 30 of these examination rooms, you can develop that overhead cloud and pop it in fraction of the time and have more trade. This is what our clouds look like today. Conference room, got the lighting on the outside, tons of different options. They're thicker. You can't see the overhead and feet quite as much. Some people like that look. Just another conference room. And this is how, so we go into the outer building enclosure. We try to design in so that some space that we can get in there. And then it's just, you can see on the upper right hand side, just you can see the dunnings right there. It's using uniform contact. GCs, we train in about an hour, basically how to lift these up. Next slide, it can show that. And it's extremely efficient. So everything's the same. We're not changing the game or the skin here. It's just that last line, that last 5 or 10%. This gives GCs an opportunity to basically own a new technology that they've never played with before to finish that last one. I think this was outspoken also. And this is probably the last slide. We're all smart label union guys, so we're not taking jobs away from the well-paid guys. This is our 14,000 square foot facility over as we can, and we're super bright. And then we've got all our engineers working in Seattle. So super cool stuff. Anyone, if you have any questions, I've got some brochures back there, cars, and maybe with this system, it's going to give some more flexibility in terms of some of the kind of gotchas with building enclosures where basically, the sensors are just right here, which really doesn't monitor what's going on over here. So we're incorporating, this is basically a smart building platform. That's the message I would say. So it just offers more flexibility and smarter opportunities for us perhaps to work with the building enclosure side. I'll end there. Thank you for that. Introduction.
Cool, Brian, thank you so much.
Yes, sir.
Got the end. Yeah, a set question and then a question.
Yeah.
There's a comment on the color. So this ceiling is black.
Yeah.
And there's still like a dark, is there a dark version of it as well?
We do, so we got a fill room up in our wine bar, so it's like 1 and 2, it's open. But we've got another design center, and we've got everything laid out, and you can kind of pick and choose colors, materials, etc. Our lead on that is Jay Miller, formerly Middle Home for 10 years, and he's got an and we'll take folks through the whole design process, and that's we'll do prototypes, doing that.
And then I noticed all the photos were like forced air distribution. Does it accommodate like
you name it. We put a picture in, well, that adds a little more weight to it, right? But that's okay. We can. It's very organized. We can have a look.
Cool. Also to take just a quick second to thank the Smart Building Center. In addition to this classroom space, they also have a great tool lending library. If you want to look at the tools to check, fan efficiencies and things like that. They have IR cameras and stuff that, guys in the envelope world know cost, $40,000 to $50,000. But they have a bunch of tools that they can loan out. And they offer this classroom space free for us as a nonprofit. So today we have Brad Carmichael from 4EA. It's principal at 4EA, originally from Vancouver. Oh man, I want to advance. Um, he's been working on building enclosures in North America for 15 years. And he's bringing us his presentation on mass timber moisture monitoring in the Northwest. Thank you very much. Hopefully this, I see it's run away.
Oh, there we go. We got catch it so I can back. Okay. All right. Thanks for everybody being here. This is a topic that's sort of near and dear to my heart. It's part of a kind of the end of a big collaborative effort from a project. Wow, is it a timed thing? Because I speak very slowly. Okay. So you guys will see that this is part of a joint paper that Jeff from my office helped write, as well as Emily Dawson from Kaiser and Path. And then it's a case study based off of a project, the Canyons down in Portland, with a lot of input from a lot of parties. And then if you'll also, there's two more important contributors as well. There's, if you've ever seen me talk, I always include a picture of my kids. And then this is some old growth Douglas fir about an hour from where I grew up on Vancouver Island in Cathedral Grove. The type of emphasis on the need for sustainable forestry management, but also the benefits that building and constructing of wood can bring to us. So what I'm going to do is I'm going to I'm going to give a little bit of a background on mass timber and moisture management. It's a an ongoing topic. I'm sure that everyone might be familiar with it. I'm going to look at some of the prior studies by others.
Sure. Slide in here and stop.
No problem. Give it a brief overview of the Canyons project and how we collected our field data. Then get into the wonky elements of hydrothermal modeling and the fun that comes with that. Some discussion of results and some conclusions. All right, how we doing?
I think that should do it. If we can just resume. Hopefully that's it.
All right. All right, let's see. Okay. So the big question is why mass timber? Okay. To ask it again, why mass timber? We'll basically, we all see the stats that buildings contribute to about 40% of greenhouse gas emissions. Of those 40%, 10% is attributable to the construction of buildings, and of the 10%, roughly 60% is structure, and most of that is concrete and steel. Basically mass timber is the only structural material that's widely used that I'm aware of that we can grow. It also results in lighter weight structures. When you build with timber, there's less weight on your foundations, less requirement for concrete in your foundations. It also allows for offsite fabrication. So if you look at this is the health science education building. The deck was panelized, and you'll see way off in the corner, there was also a composite deck with metal panel and concrete poured on it. And they were still laying rebar wire mesh. They hadn't poured concrete, but we were all ready to roof on the left side. So schedule wise, mass timber has a lot of benefits. We're ready to roof, we're ready to close the building in. Before the other side of the roof is even poured their concrete, and then they're 28 days out from even thinking about doing anything related to roofing. So schedule wise, it's a big deal. The speed of installation allows us to be a lot quicker. This building at Health Science Education Building was a combination of steel structure with mass timber decks, and then they poured a gypcrete topping on top of that. The walls were also prefabricated, so the building went up, it got enclosed, and finishes were going in far faster than on any typical ground up steel and concrete building. It's also got biophilic benefits. Studies have shown this is a healthcare education building, so studies have also shown that students learning in an environment where wood is exposed, it actually learn and receive knowledge a little bit better, react better to teaching. It's healthier. It buffers moisture, which is actually kind of cool. And it also reduces our carbon footprint. So A little bit about mass timber and decarbonization. So yeah, roughly 10% of all greenhouse gases come from the raw material production of our building structures. It's a big deal. We're another plug while we're at it. We are currently trying to get some limits on concrete and steel on the embodied carbon that goes into the Seattle building code for this upcoming cycle. If anybody would like to issue or sign on to a letter of support, please talk to me separately, because we are trying to introduce the first limits in North America on embodied carbon in structural materials, and that could happen as soon as this year. Operational carbon in our state is getting drastically reduced every year. Every energy code cycle, we're greatly reducing the operational carbon that our buildings consume. 80% of our buildings embodied carbon is in the structure, and what is usually the most low carbon material available for our structures. There are times when poorly managed forests, going back to that first slide, can result in negating the benefits of using wood, and actually your carbon footprint of a poorly managed forest going into wood frame structures can result in a building with a structure equivalent to steel or concrete. Benchmarks have shown, though, that just a straight switch out of steel to wood results in about a 30% reduction in your overall carbon footprint for your building. This is the Milgard Hall in Tacoma that you were talking about as well. Yeah, the cassettes aren't quite up there yet, though, but they're all in prep for it. So another thing of like, why embodied carbon and why now, and the numbers kind of show it, right? Our grid is decarbonized. Solar panel, national solar panel generation capacity is going up. Wind generation capacity is increasing. Every grid is slowly getting more and more decarbonized. So the national average has gone from about 950 pounds per megawatt hour 3 years ago to 850 pounds of carbon per megawatt hour this year. In the Northwest, we've stayed about the same, but Seattle in particular has an extremely low carbon grid. The electricity that powers our lights comes from very, very low carbon sources. And that's extremely important, because the more we focus on operational carbon, the more our embodied carbon starts to take a bigger slice of the pie in the overall carbon footprint of our buildings. The other thing that is really important is that even these areas, the Midwest is starting to decarbonize, you can sort of see. Their grids are getting cleaner, right? So the buildings that are in operation there, in 5 years, the electricity they consume is cleaner electricity. The steel that goes into those buildings is coal that's burnt now. The cement that is going into their concrete is coal that's burnt now. That's all carbon that's being released now. We can never get it back as long as we keep building in the meantime with all of these things. So embodied carbon is far more important in a lot of respects than the operational carbon that our energy codes focus on. Let's see here. Well, and the other thing with embodied carbon is, Seattle, it's very low carbon, and we bring in our stuff from other places. 30% of our steel comes from offshore coal-fired plants, and that's very high carbon intensity. So we're bringing in products from other places with lower carbon grids or higher carbon grids. All right, so let's talk a little bit about mass timber moisture management, because again, we want to reduce our carbon footprint. Moisture management plans, one of the downsides with wood is, as we all do it, we build in the rain. It's been raining all winter. We're used to it. We stick frame in all winter. We put, we dry out our buildings. We have processes in place in construction to, build through the rain, dry our buildings in, make sure we have the right moisture content before we start insulating and closing up wall cavities. But mass timber is a bit of a different bear. So it's much thicker, right? It's going to dry out more slowly. And there aren't really well-established practices for how to manage moisture in the meantime. And the practices vary considerably. So what you're seeing here is the ESP office buildings in Mercer Island. This is what I would consider luxurious in moisture management. Jeff will attest to that, is we were able to actually tent the building in order to dry out the wood from both sides. So it could rain all of it at once, the wood's not going to get wet. So that is one end of the spectrum. The other end of the spectrum is, end grain sealing at the plants, letting the wood come out and just hoping it's not going to rain much before you get the building closed in. And there's all sorts of incremental steps sort of in between. It becomes a little bit of a game of risk management when looking at that. What's your construction schedule? Are you going to meet it? Is it the dry part of the year or is it the wet part of the year? How wet is it going to get and where's the moisture going to go? There's not really a good established set of best practices. There are guides out there. There's also a limited body of field monitoring data out there to inform and give us evidence-based best practices. And so that's kind of what we were looking at here. So there is some field data collection in North America on CLT. So there's field data from a summer test wall out in Waterloo. Christy McClung did a number of experiments where they set up test walls in Ontario, set up like data loggers and monitored the performance of the mass timber. Then one of the first ones in the Northwest was the UBC Tallwood project, and they put data loggers to monitor the CLT there. They also noticed that moisture content spikes and rapid drying of CLT were occurring after rain events. And then there was a attempt for one of these buildings in Portland to monitor the CLT installation using data loggers that were sort of routed out and placed into the CLT. And this was at Carbon 12 project in Portland. And they monitored the CLT installation, but one of the issues that they had was by placing permanent data loggers on the CLT panels and putting them into service, water gets into the holes. It gets into the little spots where the probes are mounted, and it kind of starts to poison the data a little bit. So they ended up getting some pretty bad data results, and they suggested that maybe there's a different way to start to measure, and monitor the moisture on CLT as it's going in. So there's also been some work on the other side of the hydrothermal properties of CLT. Robert Lepage at RDH has done a ton of work doing sample measurement, characterization, and model characterization of CLT, as well as the Christy McClung work out in Waterloo. There's been some sample measurements of the UBC Tallwood projects, but then also this CLT project at Carbon 12 took some field samples of the CLT that they were going to be monitoring, and they built a sort of hydrothermal characterization of the CLT. So basically the inputs that you would use to build a woofie model using the CLT from this Carbon 12 project. That was just recent. That was in 2020. So the project we're going to talk about is the canyons. One second here. So the canyons is interesting because it's the building next door to this building, Carbon 12. Carbon 12 is the one on the left in that top middle photo, and the canyons is the one on the right. We also used CLT from the same CLT supplier. So we used the same wood sources. And then this prior study from Cordzil did all of the hydrothermal characterization. So we had all these sort of tests of physical samples of CLT from the same supplier that were used on this past building next door. They had some challenges with their data loggers getting kind of wet in place, but we had an opportunity to use the same wood producer in the same spot and try and see if we could replicate the results. So the Canyons is a 6-story, 70-unit apartment building. You can kind of see here the way that it's constructed, and that's pretty important. So it had 5 CLT floor decks over a 1-story concrete podium. The big thing that you're going to notice with this, and it can help inform practices here, is that it's platform framed, right? They didn't stick build this. They did 1 floor, and then they tilted up pre-built wall panels that were already sheathed, and then they put the next floor on top. I'm not sure exactly how you would balloon frame A 5-story mass timber building, I think you almost have to do this, but if you're doing, say, posts, a post and beam type structure like there was at Milgard Hall, you've got far wider open sides. But what happens here is the structure is kind of enclosing itself a little bit, or at least sheltering itself as it's going up incrementally. So the top floor is really exposed, floor underneath, it's a little exposed, not so much. How important is that? Well, it's not sky facing the whole time. And the exterior walls are sheathed immediately, so you've got some sheltering from wind-driven rain blowing water all over the decks. They didn't pick the best time of year to build it. Portland tends to be a little rainy, as we all know, from October to December of 2019. So the wood got wet, but then they had a dry-in process that started immediately in January, right after the roof goes on, and slowly dried the building out through April till they started filling in cavities and putting in finishes. They had a 5-point moisture mitigation plan. I wouldn't say this was the most robust moisture mitigation plan, but I think it's reflective of the fact that the building was sheltered as it was going up. I would say, and I think our peers also kind of have given the recommendation that if you're more enclosed or if you're more open on the sides, you should be doing more. But what they had here was some level of moisture planning that did still leave the wood exposed. What they did is they had shop applied sealers at the ends of the wood, at the edges, and all of the cuts. The wood was going to be left exposed upon completion, so stain prevention was it was carefully managed throughout. So the panels were fully wrapped during transportation. No non-galvanized steel connectors, which would result in red staining that you're pretty much never going to get out. No steel cutting was allowed on the deck surface. No non-water food and drinks on the floors. I thought that was an interesting one. So you could, if you wanted Gatorade through your workday, you had to drink your Gatorade down at the site office. You couldn't have it there with you next to your cutting station. So there were some regular processes enacted, but certainly you can see it. They've got peel and stick across the joints that went in same day, 9-inch wide tape on all of the joints, but that wood is out there, right? It's not sealed. There's not a membrane. It's not fully protected. They instituted a dry out phase using heat and fans that basically went to slowly bring the wood down to an average of 14% moisture content within sort of a plus or minus of 1%. So that was the drying phase before they started putting in finishes. And then a lot of masking, glove requirements, no running around with caulking guns or paints, because the wood was intended as an exposed material. Because the wood was widely exposed, and because there isn't a lot of data out there as far as like how wet can we let CLT get. It's like a Dr. Seuss run. We the group came together and established a moisture monitoring plan, similar to what we would do when we would dry in a building here, is sort of trying to make sure you're going around getting moisture probes, keeping an eye on the wood content, moisture content, and monitor the moisture from October 2019 to April 2020. The intermediate floors were monitored, and Jeff might be able to speak to the particulars of this, but my understanding is the roof went on within a week. It was on pretty much immediately, so it didn't really allow for long-term monitoring of the moisture. But the intermediate floors were exposed long-term. The BD 2100 was used, and the important thing being that the insulated prongs were used both at a 3/8 inch depth, which represents getting just below the surface of the outer ply of the CLT, and then again at the 2-inch depth, getting into one of those deeper members. One of the reasons for that is that when CLT is basically laminated together, there's a glue line that goes in between the different layers. And that glue line is important because it can restrict drying. And we'll take a look at that in a little bit. So we wanted to measure not just the moisture at the surface, but get deep enough down into the panel to know, like, is there moisture accumulating here? Is it wet just below the surface? Did the top crust just dry out and we've got wet panels that we're about to pour gypcrete on? So there were 2 depths. Weekly measurements were taken. So you can see here, by using a handheld moisture meter, you're not leaving it in place to get rained on, right? So, and you're not using a hole for your moisture probe that's going to get water runoff going down into the hole. You're building a new hole each time. Every time it was greater than 2 inches from the last hole, but more than 12, or greater than 2 inches, but less than 12 inches away from the prior location. So we had these locations sort of set up. And one of their strategy is the architect did this. One of the things with having the architect do this is they're there every week for an OAC. They walk the job, and Emily did a diligent job of being able to get regular measurements every single week at around the same time, before each OAC meeting at all of these set locations. We ended up getting a total of over 1,500 individual moisture content readings over the course of the 4 months. Certainly some weeks were skipped, but for the most part, we ended up getting this. This was originally, we call this kind of like bottom-up research, in that this wasn't a planned experiment. This was largely like a quality control process. But then at the end of it all, like, hey, we've got all this data. We got to do something with it. So yeah, we had over 1,500 moisture readings. Here's a look at the plans. So the floor plan has kind of, a bank of apartments on one side, a bank of apartments on the other, and you can see this is sort of zigzag. It's like a bridge walkway. I believe that is the canyon for which the building is named. And then there were all of the different locations, A through P, some at the more southern exposures where wind-driven rain is going to be anticipated, and then some in the central core of the building away from the perimeters, and then really well distributed kind of throughout the building. So we end up having, this is as clean as I can kind of show it, because we ended up with moisture content readings all over the place, right? But then when you take it level by level and find them on average, we find a couple trends. One, every one of those line colors is a different floor. And you can see that on average, they're pretty tightly packed. It's not like a scattershot array of random readings, and that the trends all fall along the same lines. You can also see we drew in there, this is at the 3/8 inch depth. We drew in the line of where the roof was on and the dry-in process started. And you can see the dry-in process has a significant impact on getting the moisture out of that wood, as it should, right? So you can see that the wood starts gradually drying out until at the outer surface, we're on average down below 10%, from our January 1st through April. And you can even see that the top level 6, they started putting flooring in because it hit the averages, or hit the numbers that we needed to by March. So one of the things we kind of found is you look at the start, right? The start of each one of these lines. And with the exception of level 6, which is the dark blue line, all of the other ones, the panels started at around, on average, 12% moisture content. So that means that generally through transportation, panels stayed pretty dry. So 33 out of our 34 initial readings on the first 4 floors, they were all below 15% moisture content. One reading was, at 21%, and on average, we were around 12% to start. 6th floor, I don't know what happened there. Maybe it's the last floor to go up, so it might have been neglected. The wood, it might have been stored in somewhere, in some odd way. It had 4 of 5 readings above 15%, but still an average initial moisture content of 14.7%, not too scary. But as you can see, the moisture content does go up from there. On average,
Is that the roof, or is that the 6th floor?
the roof because the roof got roofed in right away, we didn't even have time to do like moisture content reading. So the 6th floor was just the last floor right before the roof. Yeah. I know it's almost like maybe you guys should have just waited a few more weeks and let us get some data before closing in the roof. But yeah, come on, guys. No. But so yeah, that was the top floor, and I guess it was last, and maybe there was some storage issue or what have you. But on average, you know, you can kind of also look sort of at building scale, right? Like overall, our moisture content didn't at the outer surface didn't go above 16%. Okay, so on average, it's looking pretty good. There were 6 of 56 locations that had at least one moisture content reading above 20%. So that also shows protection does matter. You know, there's probably areas where you're getting ponding, areas where an open window hasn't been installed and you get some standing water. And if you don't protect, if you don't get the water off, you can see spots where the moisture content does get into that range where mold growth is supported. There were no locations above 20% for more than 2 consecutive weeks. That's also important. So getting the water off fast, clearing standing water, allowing it to dry naturally, allows you to just, maybe you have a quick spike, but nothing that's really gonna give anybody, or at least give me a heart attack on average. But there are spots where if you're getting, you know, standing water, you got to take care of it, and you have to protect the CLT in order to avoid prolonged problems.
Are they thinking stuff drying before them up?
No, because what they didn't do is they didn't start that drying process until the roof was on and sort of windows in, building wrapped, scaffolding up. Yeah, because I think they had to wait. You have to wait till you top out to really get the scaffold wrap going, and so they didn't start the drying until January. So you can sort of see. It's like that vertical dashed line is like left side, everything's slowly getting wetter. But then as soon as the drying process starts, it's like you hop on the toboggan and get all the way down.
You mentioned that you were taking these measurements as part of form. If she was taking measurements and were reading at the floodplain, were they taking actions to address it, or was she just really collecting the data?
Good question. Jeff? I think it was mostly data collection, but it was also, I think there was an expectation that if the moisture content was going to be higher, like we would all know that we might have an issue, right? Like if it's the 3rd week and we can't get this wood dry, we would have had to take different steps, introduce early drying, improve like the drying of the building, and start protecting areas. But I think the idea was, since the wood's exposed, as long as it stayed and we were keeping an eye on it within a reasonable range, that we all felt kind of okay, you know, going along. Yeah. So that was kind of the intent there. Okay. I actually learned this sort of recently. Moisture content readings got as high as 27.8, but the error is so high that I shouldn't even say it. So a moisture meter, like once you get it that high, it is totally inaccurate and it's just wet. But we did get that was the highest measured moisture content reading that we got throughout. It does show though that, you know, some parts, if you let it go, it can get wet, but the error in a moisture reader is just so large at that point. But all locations at all floors, you know, by the end of the dry-in period, were all of them below 14%, within plus or minus 1%. I think there was, but everything sort of hit that target by the time we needed our construction to keep going. So it did show, you know, we were typically within the 9 to 12% range. It did show that the dry-in was effective at getting the moisture out of the 3/8 inch depth.
Why did the level 6 stop?
Yes, yeah, good question. So as far as I'm aware, that's when they put the floor on. So they'll load the building. They're going to pour the gypcrete floor on the top floor to sort of settle everything down. So gypcrete for level 3 or level 6 went on March 11th. And so there was no readings that could be, so the readings just stopped for that floor. And then by that time, everything else was down below. And I think what drove that is that level 6 had moisture content readings all within the acceptable range to be able to be clear to, it's kind of like the same way with when we're drawing out like a stick frame building. Once everything's down below 19%, that's when you can put insulation in and start closing up cavities. The same went there, is as soon as that floor hits its moisture content threshold, then they just pour the gypcrete on and we couldn't take any more measurements. So you know, it in effect showing it was working in a reasonable schedule. Yes.
When they manufacture these members, what's the environment that they're stored at before they leave, and is it controlled with humidity? And I guess I'm curious what the comparison is when they leave the shop, what the average moisture content is, and then was the contractor required to, you know, store them until there was that mini lead time before they got installed on site? And then I'm curious if you have an overlay with like the ambient outdoor relative humidity, and how does that kind of line compared to the measurements?
My numbers.
Yes, no, because those are both two excellent questions. So how wet, essentially, what is the moisture content of the wood when it leaves the plant?
Yeah.
And then how does the moisture content fluctuate relative to ambient conditions and the relative humidity in the air, because it's not an enclosed space. Going to the first question, I believe, and Jeff, you know more about this project specifically than I do, but I believe the CLT panels leave the plant at or around their equilibrium moisture content, which is somewhere around that 12%. I think there's a range within it, and I think that's why our starting measurements around there were within that range. That said, I am going off of memory, so we can follow up more specifically. But the CLT manufacturers will typically have a range that the panels leave the plant at. And what is interesting is that the ambient conditions are very important. And I think we're going to do a little more further study, but some of the modeling we did initially was with sort of, when you do hydrothermal modeling, there's different years you can use that represent kind of the worst year, the second worst year in a 10-year period, all of these different years. And when we kind of aligned those results, it was kind of like, wow, there's no correlation at all. Like it didn't make sense. But then once we got the actual weather files from the Portland airport for that period and built our own custom weather file and put it into the model, then all of a sudden it clicks, which is kind of neat. So it does have a very important impact, even when sheltered. Now this was the 2-inch level. So this is drilling down past the first layer of CLT, getting into that second layer of CLT, and finding out what's going on in the middle of the panel. And you can sort of see, one, it's not that there's not that much change in moisture content, right? So you know, we maybe got up to about 15% on average. Everything started pretty evenly around 11%. But the interesting thing is, once the dry-in started, there's like an initial drop in moisture content, but as the moisture in the outer layers gets driven by heat to other spots, the moisture content started rising. So you can kind of see from like mid-January up through March, on average, the moisture content in the middle of the panel is going up and up and up, even though we're drying the space out. So that's an important thing to consider, is that just because you're measuring 3/8 inch down doesn't mean there's not, you know, liquid moving around within the center of the panel. And it could be increasing even when you're introducing drying. So some of the takeaways we found at 2 inches, you know, as expected, we're consistently seeing a lower moisture content than 3/8 inch depth until the end of January. By the end of January, that's when they switched, and the moisture content in the middle of the panel started being on average higher than the moisture content at the surface of the panel. That said, overall, far less variance you're seeing in the overall range of moisture content measurements that we got. We only got 3 readings at all of a moisture content above 20%. And the majority of our reading locations had nothing above 15% at all through the period, but 17 of them did have one reading up above 15%, which is where we don't want it to be for close-in. But you'll see at the far right-hand side of the graph, everything's back down on average, well below the 14% plus or minus 1 that we're looking for by the time we're pouring floors on top of that. Similar to the top crust or the top ply, none of our locations had more than 20% for more than 2 consecutive weeks. So there's a slightly elevated moisture content after January. Everything was less than 15% consistently at the end of the dry-in period. Initial drop at the start of dry-in, gradual rise and plateau. And then the other weird thing is you almost have to look at them next to each other, but there's about a 2-week shift in between the peaks and the valleys of where our moisture content kind of went. So you can even see that highest peak is on the left-hand side of the biggest amplitude of our wave on the left-hand side of start of December. But everything, the big peaks started to move and shift a little bit to the right-hand side towards the start of January before they have that drop off with the drying. And it was sort of somewhat consistently, and it's hard to show in just the overall averages, but there was about like a 2-week phase shift between when you have rain events, the 3/8 inch readings started to go up, and about 2 weeks later is when the middle of the panel started to go up. And that's just the slow process of like wood redistributing moisture within itself.
This is a question in the Q&A.
Sure. Oh, right on. Oh, I've got that somewhere. Yeah, the question is, how many days of rain occurred during construction? There were a lot of days of rain. So there was a rain gauge, and we do have a weather file. Rain definitely occurred. I don't have the number available, but I can certainly answer that sort of separately or follow up with. I just have to dig into the weather file. But it definitely saw rain, and you'll even see I've got some photos. The panels got wet. It wasn't by any means a really dry winter. It wasn't the worst, but it was. Oh, I think it reformatted my thing. Okay, that's all right. So I think there we go. I think I had it on a wider slide. So then what we did is we had all this data, and then it's this building that is right next to this paper that was done where a group had been taking samples of the CLT and establishing their hydrothermal characteristics. And we had all of the data to match with that, because we were using the same supplier, same location, right next door, and similar project team. We also, I'll talk about it a little bit more later, but we also had to make some adjustments to the models based off of research that was done on the UBC tall wood, which was starting to find like, hey, the wood seems to dry out a little faster in real life than in the models. And that's what we're going to talk about a little bit. So here's the model setup from our characteristics, just to give a brief idea of how the inputs work. So just as a bit of a background, WUFI is a transient hydrothermal model. So what it is it's one-dimensional. So you'll set up an assembly in a one-dimensional line through the assembly, assign material properties to it, assign exposure to it, and assign time basically to it, like weather exposure to it. And what it'll do is it'll give you the simulated moisture contents and relative humidities and temperature fluctuations through the assembly over a course of a period of time. It's a pretty powerful program. It's been used it was developed in Germany by Fraunhofer and used and validated on many projects and many peer-reviewed experiments. So it's pretty powerful. You can get right into the information and adjust the properties. So what we did is we actually used the properties that study from Cordzil had put together as inputs for the wood, rather than just using a library wood value to build a simulated CLT product. We also differentiated between the outer plies and the inner plies, mainly because there's the glue lines in between that affect how the wood absorbs moisture and dries out. And so then this is all based off of lab experiments that were done from the same manufacturer of CLT. Some of these are, density, porosity, specific heat capacity, are, fairly standard properties that don't change too much within wood. Some of the ones I want to draw attention to that are kind of like the things that wood is very sensitive to is the free water saturation, which is one of the big measurements of any material that you're going to do hydrothermal modeling on. And what that essentially is you basically soak a material into, in water, and it's the amount of water that some capillary active material will take up when in contact with water without added pressures or vacuums and stuff like that. I used to work in an asphalt lab where you do it with like road asphalt, make a little puck of road and soak it in water and find out how much water it takes and burn it off, find the weight, and there's your free water saturation. So it's really useful for a lot of materials, and it's just basically what's it going to soak up on its own. The water absorptive coefficient is the A value, and that is not just how much water a material is going to take up, but actually how quickly it's going to take up. So if it's going to wick up really fast, don't use it in an oil candle, because you want it to burn a long time. If it's going to be something that is going to, draw up slowly, then maybe that's something you want. Maybe it's the other way around with an oil candle. Anyways, but yes, it's the rate at which the water comes up, so versus the square root of time. Those are two critical things that the measurements do. So these are the other inputs. You'll see the liquid transport on the far left side, which is a really interesting function and one that, as you get into the setup of mass timber, increasingly the research is seeing there's things are diverging between simulations and real world measurements. So what that is it's a function of how water's redistributed in the material. So if you were to take a piece of wood and you were going to wet it with a column of water, but it's a huge piece of wood, the water is not going to go just down into the wood directly under the footprint of your column of water. It's going to redistribute throughout the material at a certain rate. The thing with woofy, and the big limitation that's becoming interesting with mass timber, is woofy is based off of like approximations that are used on natural stone and clay and porous materials that are not wood. So there's some limitations there that are really important, because what we're finding, not only did Cordzil find it, but Sam Glass from the Forest Products Laboratory did a same paper on these same panels that we were talking about, are finding that these liquid transport functions might be over predicting how water gets uptaken with wood. We'll talk a little bit about that in a bit, but what's basically happening is these models, these hydrothermal models, even when calibrated properly, even when using lab measurements of the same sort of things, they're showing, the simulations are showing water getting absorbed faster and drying out more slowly than perhaps real world measurements would show. So that's how, those are the functions for the on the top line for the interior ply. So how your liquid transport coefficient changes with your water content, but also how the RH, we'll talk about that, goes up with respect to the water content. And then how the permeability changes with relative humidity. One of the cool things about wood, it's a smart vapor retarder in a lot of ways, right? So when it's humid, it becomes vapor open. When it's not humid, it becomes a lot more vapor closed. The panel itself, you can kind of see there, it's like the most boring wolfing model in the world. So you'll see we built 5-ply panel. The darker brown is the outer plies of CLT. The lighter brown are the inner plies of CLT. We sliced the surfaces to give a 1/4 inch wide stripe at the 3/8 inch depth where we put one monitor. And then in the inner ply, we did another 1/2 inch slice at the 2 inch depth so that we were able to basically isolate. If you are ever doing hydrothermal modeling, these slices are really important because if you're trying to find moisture content at a specific location, you need to slice the material. Otherwise, it'll give you just average values averaged out over the whole depth of whatever material you're using. And it's not that useful because you might have high moisture content, towards the very edge of a panel. And even though it's showing okay on the average. So you can sort of see those thin slices represent us trying to isolate where the measurements took place. And obviously it's shown vertically, but in the model, it's modeled as facing skyward. The biggest thing with WWOOFy when modeling something like this is your rain load assumptions. And we run into this not just with like sky facing CLT exposed to that's covered by the floor above, but also like how much water is actually going to get on a wall. There's baseline assumptions that if you don't know your project that you can use, but once you start introducing things like on a wall, like canopies and roof overhangs and any areas that'll somewhat shelter, all of a sudden the fraction of rain that goes down, the fraction of rain that sticks to your wall starts to go down. And depending on the material you're using, right? So a metal panel is less water's going to stick if it's that compared to like a stucco wall. One of the things we found is that when you're doing a sky facing assembly, when you do a roof, you turn the adhering fraction of rain to 100% of the rain lands on the panel, right? If it's totally sheltered, like that job where we had the tent over top and you want to monitor just the ambient moisture that's going to be going through there, you put down 0 rain, and then it's just ambient humidity that's going to impact your model. But what about a platform framed building where the floor up above is partially covered and you got open windows and different levels of rain that are going to be hitting the panels? So what we ended up having to do was like a sensitivity analysis and found that like how much water hits these panels impacts the predicted amount of moisture content very, very significantly. So if you have, and we'll even show like past studies for like canopies and sheltering effects show that basically 80 to 100% of the rain doesn't hit the wall when you've got a 4-foot canopy. So when your floor is, you're taking measurements 4 feet in from the walls, there's not a lot of rain that's going to be hitting these panels on the lower floors. And we did find that we had to have very low amounts of adhering fraction of rain, like hitting these panels in the simulation to get our peak moisture contents down to 18.6. Now, we'll kind of show it in a graph later. None of our average numbers got close to 18.6 on average. So the simulations are showing really wet panels, right? So this is where we're at with overlaying how a WWOOFy model simulates these panels with the weather, with with very little rain exposure compared to how we measured everything. So just to explain the graph a little bit, the red line represents the moisture content that the WWOOFy model would simulate as your moisture content in the 3/8 inch depth using our weather file. The black line is the average moisture content. And then the light brown top and bottom is one standard deviation away. So it's the majority of our measurements fell within the bounds of that, fell within the bounds of our, those two light brown lines. And what you're kind of seeing is that the simulation, even with, this is the simulation with, basically 5% of rain droplets even hitting. And it even looks like this when you go down to 0. Even then, the moisture content is more than a standard deviation above our average measurements. So it's predicting quite high levels of moisture content compared to what we were measuring. So our key findings, and you can see, I mean, that's more than 5%, right? Like floors got wet. The simulated results generally show higher moisture content than what we were measuring, even sometimes more than one standard deviation away. The peaks and valleys you're seeing there, like they're generally correlating. So once you introduce a weather file, it actually does start to follow. When you use a standard weather file, it's a very different alignment. Compared to the simulation, we had faster drying rates. And as you'll see, remember, I didn't have the black dash line, but clear divergence in the simulation and the measured results once drying is introduced. So the divergence there is kind of what shows us the impact that the drying process has on reducing the moisture content of the wood relative to just leaving the wood alone on its own.
Simulation doesn't account for drying at all.
It doesn't, no. There's going to be a next step to this where I'm going to build a new weather file that takes all that rain out and then keeps a steady heat. And then I'm going to see how it aligns. But for the purposes of this paper, we just wanted to see the divergence and the impact that the drying did. Why is it not? Doesn't seem to be. I might have clicked out, perhaps. Here we go. There we go. Okay. And so, on average, it's good news, right? Like the results were actually more optimistic than what the model is showing, because the model is showing us something that's quite conservative. So it ends up being quite good for us. If you look at the simulation at the 2-inch depth, you'll see that our measurements were all up and down and all over the place. But the simulation shows kind of a nice gradual rise over time. And that gradual rise, we did see a little bit, but this also shows that, at least simulation wise, the Wolfie model expects that center panel to increase its moisture content by about 2%. We did see that similar kind of rise. So that's important to note, but we also saw a lot more fluctuation in our measurements, because these are average measurements of 1,500 measurements, or of our 1,500 measurements in our 57 spots. And we're showing far more deviation or far more amplitude in our line than what a single line simulation is. Usually it's the other way around. Once you average things out over a large number of measurements, it's a smoother line than a single simulation. But there's some importance there. So that the fact that there's less dampening of the moisture content kind of indicates that the wood, the moisture is actually moving around a lot more quickly within a panel than what the simulations are showing. The muting was actually shown in past studies of it seems here that the simulation kind of mutes the level of liquid transport within the wood panel over time compared to how you would actually measure it. So there are similar trends in research that it's showing, and it shows that distinct drop in moisture content after drying produced compared to the models. You can see the difference between the black and the red once heating is introduced at the start of January. So what's going on here? What is really cool? It's up to about 99% humidity. And even after that, most of the water in wood is actually bound in the cell walls. It's not really liquid water. It's called bound water. And that's why wood shrinks and swells and as it gets wet and it dries. It's not actual liquid water that's sitting so much inside the wood. But once you hit about 99.9% relative humidity, the overhygroscopic range, the moisture content, that's when it starts to sort of shoot up. Okay. Natural stones are what woofy is based off of. Those don't have these like volumetric changes or bound water that wood has. So they're able to reach, like in a lab, saturation pretty easily and pretty quickly. The other thing that we see with wood compared to the materials that woofy is based off of is the wood has a cell structure. It's kind of like a closed cell structure in a lot of ways, and that traps air, and air resists like the intake of water. So what we're seeing, or at least what some of the research is showing, is that the numbers you see in a lab from the saturation tests are actually a lot to do with the vapor permeability of wood changing over time and not being accounted for because the models are based off of stones and masonry products that don't change in permeability as they get wet, and so they just neglect the input of vapor permeability. And so the amount of water that a model is assuming is double counting the amount of water due to the permeability of the material. So your wood is anisotropic, straw is bundled together. The uptake in the side of a panel is quite low. It undergoes volumetric changes, and the permeability changes with increasing moisture content. The way that the suspicion is, or at least some of the published work out there, is questioning whether or not vapor diffusion is getting sort of double counted in a woofy model. And the kind of implications of that are that it's giving us over conservative results if we're going to be modeling things like mass timber and how it reacts to moisture. Why is this important? Because we need to have really good, well-informed ways of simulating or anticipating the impacts of moisture on our wood if we're going to be building with mass timber in the Northwest, right? We can't stop construction schedules in October because we're afraid of wood getting wet. If we're going to start moving away from concrete and steel, we're going to have to live with the reality of mass timber going up in December in Seattle and how we're going to deal with that. Over conservative modeling may inhibit the use of mass timber. You may have contractors that get afraid to, use a new material because, we don't know how much rot we're going to get if it's out in the winter all winter, or out in the rain all winter. And it also informs resource allocation. Like what we're sort of seeing is the bang for your buck is not necessarily protecting the sidewalls of your panels, but it's preventing stains and put your resources towards protecting your end grains, protecting your joints, protecting the stains, upgrading your hardware so that you don't have ungalvanized metal. Put the resources into those higher end things, protect the wood, make sure if you've got cracking that you're keeping an eye on it, and always have a quality control program where it's very easy to have someone like a field engineer or a project architect that's there regularly taking moisture content readings and keeping an eye on it. So we know that staining still occurs. All those moisture content readings, they don't really matter if the wood's really stained and people want to look at it. So that all happens near the surface, and so that'll still occur regardless of how wet it gets in the middle of the panel. And then joints and end grains, because it's straws, those are far more susceptible than the sidewalls we see with our CLT. So some of the conclusions are, we're seeing that simulations show a little bit of faster drying out and faster wetting of CLT compared to what the measurements show. So under prediction of drying has been noted by sort of us, as well as a lot of other papers that have been done and are still being done. We believe it's related to software double counting vapor diffusion, it being CLT being non-homogeneous, and then further work sort of needed. Generally good agreement at a 2-inch depth between field measurements and simulations. And for the software to be conservative, it's not a bad thing. It's just we got to be aware of when we're getting false negatives and software telling us things that are going to be, horrendous when maybe in reality they're not going to be. The amount that adhering fraction of rain showed how sensitive the panels were is important because it reinforces that protection matters. If you can platform frame and get another frame up above, get the roof on quickly, get a drying process started, that'll go a long ways towards keeping your wood at a reasonable moisture content. And then dry out more. So you can reasonably get that wood drier by introducing a long drying process into your construction schedule of a couple months and get yourself into a range safely where the wood's okay to cover. And that is it. And have any questions? Yes.
It's been 2 or 3 years that you had any callbacks, you had any issues with the panels since the building's been open?
To my knowledge, no. Yeah, and the other good thing is that building was the second building by the same developer, and so that developer who built Carbon 12, it went well. They didn't have any issues, so then they went and built the other one right next door to it. So the lack of issues was enough to give the developer confidence to do the same thing. And we weren't on Carbon 12; we were on the Canyons, and there was a degree of confidence in the team of everything went fine on Carbon 12. Let's take care of the joints, have a plan, monitor moisture. And we were kind of ooh, it's Portland and it's the fall.
Do you see this coming up in Seattle or what?
Yeah. I think some of these projects, the Milgard Hall was Tacoma, and then the health sciences is over at UW's campus. I think, was it Fordham Hall? So the University of Washington is building quite a bit with CLT. We're seeing some more CLT, the ESP offices, and it's certainly going to become more prevalent in our marketplace. Our code has just changed in Seattle to allow CLT up to 18 stories. As mentioned earlier, there's hopefully going to be restrictions on the amount of carbon that goes into concrete and steel, which will help, also incentivize the use of alternative structural materials like CLT. So there's a lot of good things happening. It's materials we grow regionally. It's renewable. As long as we're managing our forests properly, there's an ample supply of wood for our region. It's good for our economy. We do have a healthy forestry industry in the Northwest, and so it beats importing cement from China as far as I'm concerned. So I'm a believer of of the system.
Do you see parallels or divergences between the CLT you talked about here and DLT and NLT panels?
Yeah, so because the glue lines matter, right? So there's with things like DLT and NLT, you've got a lot more interstitial space where liquid water can just get trapped in between. And the same sort of goes with CLT. In that, if you get cracking, if you dry it out too quickly and you get cracking and it gets wet and you get water trapped. So perching of water is something that needs to be looked out for and cautious with. And I'm a little bit, I think I'm a little more hesitant with the DLT and NLT because of that the non-laminated gaps and a little more ability for interstitial water to go in between. But that said, that's just mostly speculation.
Looks like there's another question there.
Oh, great. So the question is, floor levels are able to dry out, but is there a process to allow the roof to dry out? Yes. There's various ways. Some of the ways are the strategy that was implemented on this project was pick the roof in a dry week and get the roof on right away. I think that's kind of what it was. I think there were some, remind me again, Jeff, I think there were some sort of vents, but yeah.
Paper barrier went down first. They put in, I think, about 6 of 8 paper boards.
Yeah. Yeah. Pre-applying, if you are going to be putting CLT up in a under wet conditions, and I think Graham will be talking about this more at the symposium, is pre-application of membranes before you put them on the roof, and then just seaming it right away is a reasonable way of protecting the CLT if it's really wet out. A lot of the jobs we've had have been scheduled to be like a dry window when you pick the roof and get the membrane on right away. And as long as you're not saturating that wood, the hybrid redistribution of the CLT allows you to just absorb, 2% moisture content increase in the middle panel, but not really something, as long as it's a dry period and you get the roof on quickly, that's one way of protecting it. If in doubt, put the membrane on before you put the panels up on the roof, and then just come in and stitch the seams and complete the job.
There's also
Overbuilding, and I think that's a good contingency plan if it gets wet. I wouldn't necessarily think that's the first plan. It's sort of the second plan of your measuring moisture, and the CLT panels get really wet and you can't put a roofing membrane on, then you overframe with sheathing and furring so that you can introduce air movement between the surface of the CLT and the underside of an overframed sheeting board and allow it to dry back into the interior. I think our Vancouver office did that at one of the projects in UBC where the wood got really wet, overframe, roof, and then dry back into the interior.
Is there what's the cost differential between concrete steel structure versus CLT structures?
Good question.
Is there a rule of thumb?
Yeah, that's a really good question. So I want to go back to let's see here. The health sciences is a good example. So because there's projects where, and if I remember correctly, with Founders Hall at UW, my understanding is that CLT wasn't the most cost effective, but it was close enough that the team went with it anyways. I'd say that it should be something to be careful about taking the costs in a silo. Because health sciences was the one where the team planned from the beginning to beat schedule. So sometimes the biggest cost in your construction project's not the material, it's the schedule you're fighting against. And having the CLT panels, and this is actually why we didn't put a temp membrane on, is what they ended up doing is just rolling a flatbed truck up to site, picking the panels in place and getting them in and keeping the building moving and getting it enclosed right away. So they picked up on schedule by not having to wait for rebar, not having to wait for all of concrete to cure before you can get flooring in. They pre-panelized, so we hung pre-panelized walls that were waterproofed in a plant. Those also came off the flatbed of a truck. So everything on this job on the enclosure was essentially pre-panelized. And you take that and you work that into the schedule, and it's difficult to quantify how much you save over the inevitable schedule delays you have of not getting a rebar inspection passed, or you know what I mean. So yeah, it's tough, and I don't know that there's enough data out there to really know how much got captured, but because you can pre-panelize it, there's a potential for so much more efficiency there. Especially, I think, not necessarily as a vertical structural system, but as a horizontal structural system compared to conventional metal decks and concrete slabs. I think there's a lot of potential.
Is that structure slope?
Yeah, we sloped the structure down to a valley. So, and again, it simplified our taper plan on the roof. And again, we didn't really, so we just had sort of diamond crickets along the Central Valley, and off we go. But yeah, it was cool to see, and we can find it, is that the other half of the roof they ended up doing a conventional roof, and they were roofing it way later. It was way behind in schedule because it took so long to get that roof ready to get the roof on, and that drives interiors. And they were able to get interiors going underneath this roof way earlier than they were able to get interiors going on the west side of the roof, where they were having to wait a long time. So those benefits, those sort of intangibles are really important because that's where a lot of the potential is. Whitney. Huh? Oh, I know. Let's see here. Hey now, Nathan. That's supposed to be low. So I may or may not have a building science themed Twitter account, but I don't know if I can edit it. So it says, look at all these great modeled results, and they're looking over, the kingdom, and measured results are really where the truth and all of the dark secrets are put, whether it's energy models, woofy models, or anything. It's easy to make model results look good. The reality is sometimes measured results are, we see it with air tightness, we see it with, window testing, anything. By the time we measure and test, that's when we start to see all the the dark side of things.
I feel like you do your work at Disney,
Thank you so much, everybody, for coming out.
All right, thank you. Happy to be here. And I also don't mean to be rude, but I am going to jet out the door because I promised my kids I'd take them to the Kraken game, and puck is dropping right now. So I will leave some cards here, and we'll spend hours answering questions at another time, but I did make promises to children. So thank you all so much.
Yeah, thanks for making the schedule work. Oh, great. Thank you.
Okay.
Go crack.
Absolutely.
Oh, I forgot to say, if you didn't sign in, I would weigh in to make you sign in. I know there's some like arrival stuff. Thank you, sign with that. Be great. Thank you. I know.
I think that's everything. Yeah.
All right. Thanks so much.
Yeah, thank you again.
Fast.